of the problem by 1. So this is the use of reducer concept, this kind of day-to-day problem. In fact, it's already using reduce and conquer. Okay? So every time, each time you reduce the number of effective key, it means the size. In this case, the size of the problem. If you have n key, the size of the problem is n. Okay? So first step, you try one key. Okay? Try one key. By trying one key, if it's not a key, then the next round you have to try would be n minus 1 key, right? We have 1 key less. So you reduce the size of the problem. That means the next step, you need to solve. That means by solving the size of n key, you solve the size of n minus 1 key. So you don't need to try the key that you try next step. Reduce the size by 1. So this is the use of reduce and conquer. Okay, here is just a story. The goose is a fear beast. Live in the dark forest. Something like a monster. It's a monster in the dark forest. It's very dangerous. So now the problem is to build a group fence, group-proof fence, so that you'll be safe. So it's invisible. It's very difficult to see, but now you're going to use a blue horn. Blue horn will bark. Then we can sense it. You will bark when you come closer to the monster. You will bark. So we are going to use this one to blue horn to help us to build a group-proof fence, so that to fence the monster in a small enclosure, so that it is safer. Okay, so this is the use of reduce and conquer. Yeah. So the method is very simple. Okay, our aim is to trap the monster, the goose, in a small section in the forest, because it's very dangerous and it's invisible somehow. So we use a reduce and conquer method by using a glue horn to help us to build a group-proof fence. So initially it's a whole forest. So then we use a glue horn to detect whether it is in this area or is it in this area. Okay? So one glue horn detect that it is this area, it's one of the area. So we are fence up. Fence the monster in one of the area. Then that means every step we reduce the size of the problem. Initially is to the whole forest. Then this step, after the first step, we build a fence here. Okay, so we trap the monster in one of the area. So the problem size is reduced. In this case, reduced by half. So reduce and conquer. When you use the reduce and conquer, when you decompose a problem, the size of the problem may be reduced by half. It may be just reduced by one size. It depends on the problem. In this problem, we reduce by half. Then again, if the area is still too big, not small enough, then again we will use the glue horn again to detect whether it's in which part of the forest here. Okay? So once the glue horn detect it, we can cut this one into half again. Cut this half into half again. Okay? So let's say if it's one of the area, if it's somewhere here, we can just cut it here. So so you will fence the monster in one smaller area every step. So we'll continue this operation. Continue this one. Then here again we use a glue horn to find out which area. Again we'll fence up again until we fence the monster in a very small area. Then we will stop. So continue to fence until it is in one of the area. Yeah. So now this is small enough. So we will fence up the area. So this also to reduce reduce and conquer. Every time we reduce the size of the problem by half, we reduce the size of the forest by half. It means we need to search only half of it. Okay, each step, one section, then after we fence it, we only need to examine the section that the monster is there. The next step, we will examine the section. Then we examine until we reach, we fence it to a small enclosure. Okay. Now we're coming to Egyptian fraction again. We discussed that during the greedy approach. Egyptian fraction means for any rational number, this is a rational number, we express it. We express it as a sum of. We express it as sum of many numbers. Okay. We express it as a sum of many numbers, all with numerator 1. All with numerator 1. All these are my ex-students. Okay, any fraction, we convert it to a series, the sum of a series of fraction, all with numerator 1. That is Egyptian fraction. Yeah. So this is Egyptian fraction for 3/4. Okay. Any rational number can be converted to Egyptian fraction. Okay, the strategy here is we adopted was repeatedly find the largest 1x fraction. That was less than or equal to the remaining part of the original number. That's what we do in when we discuss greedy approach here. So initially we find the largest fraction in the form of 1 upon something that is smaller than the number, right? So and then after that we do the same thing again for the remaining part. So if you look at this another way, okay. Earlier we are trying to find, then we do not really express it in terms of algorithms. Here, okay, the Egyptian fraction of rational number are by finding the Egyptian fraction of the rational number that is smaller. So actually, now it is still based on the same method we discussed in greedy approach. So we find, so every time we reduce the size, we look at the problem there. So we define some notation here. We define part f. So initially it's f. F equal to xy. It's a rational number. Any rational number can be expressed as a fraction x upon y. So part f is the largest fraction with numerator of 1 less than or equal to f. Okay? So that's the meaning of part f. That means the part f of part 3/4. Okay, what is part 3/4? The largest fraction in the form 1 upon something that is less than this value. Okay? 1 upon something, 1 upon n. Largest fraction in the form 1 upon n. Okay? So which one is the largest? 1 upon 1 is the largest already, right? 1 upon 1 is 1. Cannot be larger than 1 upon 1. Yeah. So is 1 upon 1 less than this one? We have to find something less than this value. That's the meaning of f. Find the largest fraction that is less than this value. 1 upon something. 1 upon 1 is larger than this one, right? So part 3/4 cannot be 1. 1 upon 1. So what is part 3/4? After 1 upon 1, what is the next fraction? Which is in the form of 1 upon 1. Okay, we talk about 1 upon n. The largest one is 1 upon 1, right? After 1 upon 1 is 1 upon 2, right? Right? 1 upon 3. When grow bigger, when the denominator bigger, then certainly the value is smaller, right? So this is the larger, this is second largest, right? So this one, the largest one is already exceeding the 3 upon 4, so cannot. What's the next one? So 1 upon 2, is it the largest fraction? That is less than this value. 1 upon 2, is it the largest fraction? So is part f, part 3 upon 4 equal to 1 upon 2? Is it equal to 1 upon 2? Yeah, you got the right answer. Is it? So the next fraction, the next larger fraction is 1 upon 2. Yeah, 1 upon 2 is less than this one. And that is the largest function. Because this one cannot, this one is not. So this one is already exceeding this value. Yeah. So the largest fraction, 1 upon something that is smaller than this one is 1 upon 2. Okay, here, some definition. We actually part this particular function, part x upon y, you can calculate in this way. By looking at this way, we know that part 3 upon 4 is 1 upon 2, right? By examining. But actually, part f can be calculated. Part f is equal to 1 upon the ceiling. Ceiling of y 4 upon 3. So that is 1. Okay. Ceiling of 4 upon 3 ceiling. What is the value? 4 divided by 3, the ceiling. The ceiling is the integer, that is the smallest integer that is larger than the value. 4 upon 3 is 1 point something, right? 1 point something, the largest integer that is the smallest integer that is larger than 4 upon 3. Ceiling means the smallest integer that is larger than this value. What is the smallest integer that is larger than this value? Can you have some answer? What is the smallest integer that is larger than this value? Ceiling means the smallest integer larger than this value. This is the notation to represent ceiling. 4 upon 3 is 1 point something, right? 2, yeah. So it's 1 upon 2. Okay? So actually you can find out this. So part f can find out from this. It's 1 upon 2. So ceiling. This is the formula to calculate part. Earlier we didn't go through this kind of function. So ceiling, smallest integer that is greater than y upon x. Okay. So the formula is when we calculate part x upon y, we have to take this one, 1 upon ceiling of y upon x. Chain, interchain x and y when you calculate the ceiling. So that's 1 upon 2. So that means the first term for this one, the first term in the Egyptian fraction, it should be 1 upon 2. Okay, now we calculate. We see this, calculate this Egyptian fraction for this one. So the way we calculate Egyptian fraction, that is also the same way as what we did when we discussed the greedy approach. Is to find the Egyptian fraction for a rational number f. Firstly, we check whether f is 0. If f is 0, we stop. Nothing. Okay? If this is the base case, when f is not 0, we write down part f. Write the part f down. Okay? Part f is using the function 1 upon ceiling. If f is x upon y, then part f is 1 upon ceiling of y upon x. The other way around. Right now, part f. Then after that, find f minus part f. Okay. So this is the way to find Egyptian fraction. This small algorithm is to find Egyptian fraction. Okay, and you can see that this is a recursive algorithm. Find this algorithm here. One of the instructions in this algorithm call the algorithm itself. Find, yeah. That means this is call itself. That means this is a recursive algorithms. And now we see how this algorithm works. Okay. So if we want to use the algorithm to find the Egyptian of 4 upon 5, the first time, yeah, you will find part f, part 4 upon 5. Part 4 upon 5, follow the formula is 1 upon ceiling of 5 upon 4. That's 1 upon 2. So there's the first term. That's the first term. After that, you write down the first term. Write down the first term as the Egyptian fraction for 4 upon 5. After you write down the first term, then, so we have found the first term already. So now, we have to continue to find. Originally, we want, this is to find the Egyptian fraction of 4 upon 5. Now, we have concluded, after we use a part f function, we have concluded the first term should be 1 upon 2. Okay? So, since the first term is 1 upon 2, that means now, the next step, we will find Egyptian fraction for the remaining value. 4 upon 5, since you already find the first term, so you will subtract away the first term, right? 4 upon 5 minus 1 upon 2. Then this is the remaining value. So next step, we will find the Egyptian fraction for this fraction. Okay? So this is smaller. So every step we get closer and closer until we reach 0, right? So here you can see the 3 upon 4 certainly is smaller than 4 upon 5. So it's a smaller problem. So in other words, we solve the original problem, okay, by solving smaller subproblem, 3 upon 5. To find the Egyptian fraction for 3 upon 5, it's a smaller subproblem. So in this case, the size of the problem is measured by the value, okay? So now the second step, we will find Egyptian fraction for this one. That means to find Egyptian fraction for this one, that means we execute the same algorithm again. Okay? So solve for this one. Instead of solving this one, we solve this subproblem. Okay? So continue. So what we must do is to find the part f. Part f, apply the formula, substitute into the formula. Part 3 upon 10 means 1 upon the ceiling of 10 upon 3. So that is 1 upon 4. That's 1 upon 4. So that means now we find another fraction in the form of 1 upon n. That's 1 upon 4. So that means this is the second term. This is the second term of our Egyptian fraction. Okay? So we want to find this, but this is a number, this is the largest fraction in the form of 1 upon n we can find. So that means now the next step we will find Egyptian fraction for 3 upon 10 minus 1 upon 4. Okay. So every step will reduce the amount, the value we need to find. So after divide, you'll find that after subtract away 1 upon 4 from 3 upon 10, we get 1 upon 20. 1 upon 20. Then the next step, we will find Egyptian fraction for 1 upon 20. Okay? 1 upon 20, the Egyptian fraction is actually 1 upon 20 also. Okay? After you apply the same formula part f, then you write down this one. So now, since now the Egyptian fraction find for 1 upon 20 is 1 upon 20. So what is the remaining amount? The remaining amount will be this minus this is 0. It's 0. So 0 it will stop. So here, this for finding Egyptian fraction of 4 upon 5, all together we okay. So 4 upon phi. So altogether we generate one call, one recursive call here. This is the original problem. To solve the original, that is not a recursive call. We generate one recursive call, two recursive call here in order to find the, then here generate another recursive call, three. 1, 2, 3. Solve means call the same, solve means solve the same problem. Solve the same problem means call the same algorithm. So in other words, this algorithm is designed using reduce and conquer approach. Okay? So if the rational number is not 0, we will do this, we write down part f. We will find one term of the Egyptian fraction using part f. After that, the remaining value, we will, then after that, we find Egyptian fraction for the remaining value. So the value getting lower and lower. So we, then towards the end, the remaining value will reach 0. Then that is the Egyptian fraction. So this is the algorithm for finding Egyptian fraction, and this is the use of reduce conquer. You can see that there's one sub-problem here. So in order to solve the original problem, f, find Egyptian fraction of f, we solve a smaller sub-problem. Okay? Find f minus part f. F minus part f is a smaller value, there is a smaller sub-problem. Okay? So we solve the smaller sub-problem and use that smaller sub-problem to generate the solution for the whole problem. So this is the use of reduce and conquer algorithms. Okay, we have discussed this, and you will find that, okay, after you execute this algorithm, you will get these three fractions. With those fractions we write down 1 upon 2, 1 upon 4, and 1 upon 20. All these three add up together will be 4 upon 5. 4 upon 5 is exactly equal to this value. Okay? So this is the way to find Egyptian fraction, the formula. Okay. Now we shall proceed to another problem that we can use reduce and conquer. That's the problem. Computing power mn. Calculate. We can write algorithm. We can solve the computing of this number. We can solve the calculation of m to the power n by using reduce and conquer. Okay? Why? Okay? If you study the formula for m upon n, you'll find it. M upon n is 1 when n equal to 0. And here, okay, in this case, n is the size of the problem. Okay. The higher degree, the harder to find. You will have to do more work. So if you want to calculate 5 to the power 3000, that is harder than 5 to the power 10, right? So mn in terms of power, if n equal to 0, regardless of the value m, it is equal to 1. Okay, so now we study this formula. How about when n greater than 0? If n greater than 0, we can decompose this problem, I mean the calculation of m to the power n, into two parts. Okay, m times n minus m times m to the power n minus 1. Right? Again, this is the formula. Take one m out, then here the m would be to the power n minus 1. Okay? So 1 degree lower. And this is computing, this value is also a problem. It's also an original problem. Okay? Originally, we have to compute m to the power n. Okay? And the computation of m to the power n minus 1 is the same problem with one size lower, right? So if you follow this formula, that means we are computing m to the power n using reduce and conquer. Instead of computing the power mn, we compute the power mn minus 1 and use that to calculate the value for m to the power n. Okay? So this is a very simple formula, but it is the use of reduce and conquer. if you write in algorithm, this will be the way. M, you want to calculate to the power n. Okay, so follow this formula, you can specify. So if n equal to 0, that's a base case. Base case, we return 0, return 1. If not, if n is not equal to 0, that means more than 0. Then we will compute m to the power n minus 1, right? Compute m to the power n minus 1 is a problem of smaller size. So it's a problem of smaller size. So we will solve it using the same algorithm by substituting different parameter. M here n minus 1, one size smaller. M times this one. So in this case, we are also solving the problem of computing m to the power n. Okay? From a smaller subproblem, this is a smaller subproblem. So from originally we want to compute m to the power n, but we compute m to the power n by computing m to the power n minus 1. That is one size smaller. Then use the answer for this to form the answer for the original problem. That is m to the power n. In this case, it's straightforward. Just use the answer for m to the power n minus 1 times n. We will get the answer for m to the power n. So this use of this reduce and conquer. That means we solve the original problem by solving one smaller subproblem. This is one smaller subproblem. Okay, and this way, every time we do just like 1 degree, it is very slow. If we want to compute such number, 2 to the power 1,000. Okay, so that's a very big number. Every time you reduce by only by 1, then you have to reduce many times, 1,000 times. So maybe we can make it faster. Yeah, we can make it faster. Okay, so we can restructure the formula. With n equal to 0, it's still the same. Mn is still 1, but when n is even, we can compute the value for mn divided by 2. Then use that square. That will be m to the power n. Okay, if n is even, that's it. M is a value. So to compute, in other words, to compute 3 to the power 100. Okay, we can compute 3 to the power 50. Then square, take a square, right? So that's if it's even. If it's odd, we cannot. We cannot divide by 2. We cannot do it this way. So if it's odd, we go down by 1 first. Go down by 1. So that means if it's even, we reduce the degree by half. So now we can, based on this formula, we can design and reduce and conquer solution for computing m to the power n. To make the computation of m to the power n faster, because very often, especially in security, we need to compute value for very high degree. Okay? So this is the way we do it. If it's n equal to 0, the same thing, the smallest one. If it's even, okay, now we call it better, faster, power fast. Okay, faster because we every time reduce the power by half. Okay, so this is to compute m to the power n divided by 2. If it's even, so if it's even, n is divisible by 2. So we compute this way, then after that we take the square, right? So this times this again, then that means square. So we get the answer if it's even. If it's not even, that means if it's odd. If it's odd, we just reduce by 1. That's okay because odd you reduce by 1, the next time will be even. Next round will be even. We'll follow this. We'll follow the action here. Reduce by half. Next round. So if it's odd this round, we just reduce by 1. So if we reduce by 1, odd will be even. then next round we can follow this branch. Okay, and this is also the use of reduce and conquer. Okay, that means we solve the problem of computing m to the power n. In this case, we want to solve it faster. So we reduce the size of the problem to a larger extent, reduce by half. Okay, for every alternate case. Okay, then so this is calling the same algorithm for a much lower degree. Okay, this is a one subproblem. Okay, this is a solution for one subproblem, and we use the solution of subproblem to form the solution for the original problem. And here, you may wonder why I say this case is reduce and conquer, since we solve this problem and solve this problem. No, we don't solve two problems. Every time we only solve one problem, because n can be odd, and can be either odd or even, cannot be both. So if n is even, we will solve the problem m to the power n divided by 2, if n is even. Okay. If n is odd, we will solve the problem of m to the power n minus 1. So it's two different subproblems, but each time we will only use solve one subproblem. It's not two subproblems. So this is also the use of reduce and conquer. Okay, now we proceed to divide and conquer. As I highlighted to you earlier, okay, if we divide the problem into multiple subproblems, means if we divide into more than one subproblem and we solve each subproblem, after that we use the solution, after we combine the solution together to form the solution for the whole problem, then it is the use of reduce and divide and conquer. In other words, the difference between divide and conquer and reduce and conquer is that divide and conquer decompose a problem into multiple subproblems, means more than one. After that, solve all the subproblems, then use the solution for the subproblem together, combine them together to form the solution for the whole problem. So, so the difference between the reduce and conquer and divide and conquer is that reduce and conquer is just solve one subproblem, smaller size, but divide and conquer solve multiple subproblems. Here, computing power, again, we can just now earlier I show you how to use reduce and conquer. Yeah. Now, computing power can use divide and conquer as well. We can restructure the formula in this way, right? So m to the power n can be expressed as m to the power floor n divided by 2, and time m to the power ceiling divided by 2. Okay. Just see an example. Okay, take for example, let's say this one. M Vt, in this case, means if we use this formula, three to the power 100 will be first 3 to the power 100 divided by 2. 4 times 3 to the power 100 ceiling 100 divided by 2, right? So floor 100 divided by 2, how much? 50, right? Ceiling also 50, right? So in this case, it's 50 times 3 to the power 50 times 2 to the power 50. How about this case? 101. 3 to the power 101. Then the first part is floor of 100. Okay. So we use this one, then 3 to the power 101. floor divided 101 divided by 2 floor and 3 to the power 101 divided by 2 ceiling. So this is how much? How much? This one?
55.5 or 50, I don't know.
50 point something, right? 50 point something floor. 101 divided by 2 is 50 point something, right? 50 point something. So the floor of 101 divided by 2, what is the floor? What is the floor? Floor is the largest integer that is below the value, right? So, go to, this one is 50. 101 divided by 2. The floor, 101 divided by 2 is 50. How about the ceiling? Ceiling have to be larger.
51.
The smaller in. Again?
51?
Yeah, 51.
So run up, run down.
Yeah. So exactly. So use this way, you can divide into two parts.
Is it 3 to the power 50 times 50?
Oh, 3 to the power 50. So it is 2 to the power 51. So this is, after we structure in this way, then we can write, we can solve the problem. Based on this formula, we can calculate m to the power n using divide and conquer. So two sub-problems. This is a sub-problem, and this is a sub-problem. Okay. Both are smaller than the original problem. Okay, now we have a divide and conquer algorithm. So if it's 0, return 1. If it's not, then return, this one is 3 to the power, this one is a to the power, ceiling n divided by 2. This one is a to the power, this a to the power floor divided by n divided by 2. This a to the power ceiling n divided by 2. These two times together. Okay. So two sub-problems. Okay, when we want to solve, when we want to calculate a to the power n, we have to do this. This is a sub-problem. This is a solution of the sub-problem. Okay? And this is a solution of second sub-problem. Two sub-problems. We have to solve both sub-problems. Solve both in order to calculate the a to the power n. Right? So two sub-problems. In this case, it's the use of divide and conquer. It's different from the earlier. Get it? Understand? The difference between the reduce and conquer and divide and conquer. So now here is talk about calculating the permutation element in a set. So let's say if the set has 3 names, these 3 names, 1, 2, 3. So now we want to calculate calculate all the permutation. These are all the permutation, all the different arrangement, between these 3 names. Okay. And then quiz. Then the other one, all together they are okay. So since we have 3 items, all together they are 3 factorial way to permute the 3 names. Okay. So these are the permutation of the 3 names. Now we want to work out a method. To compute all the permutation. Given a set of elements, we want to work out a method to do all the permutation. Our problem is to find a strategy for list all the permutation one way. Okay? So here need a little bit of notation. Let S be the set of n elements. Okay? So we want to, given a set of elements, we want to find the permutation of all these elements. Okay? So in this case, it's n factorial. n factorial. If it's n item, it's n. Just on 3 item already got 6 permutation. 3 factorial is 6. So it's quite a large number. Okay, we have some more notation. Si is to be the set of that. If we remove Si that means excluding, if it's S2, that means the remaining set element excluding S2. Okay, here we have an example. So in this case, S1, if you have 3 names, S1, the first one is S1, Tom, the second one is Dick, the third one is Harry. Okay, then what is S2's asterisk? S2 asterisk. Okay, so here S2 asterisk means excluding the second item, excluding Dick. So the set excluding Dick, Tom, Harry only. Okay, S2. If it's so we have this notation. So and we have some. If you look at it carefully, you will know that every permutation of this, the permutation of these 3 names, okay, if you look at it again, the permutation of these 3 names, okay, is the combination of is a combination of permutation start from Alan, start from first name. Okay, these 2 are the permutation for the permutation start from Alan. The other one is the permutation start from Bob, right? Then the last 2 is the permutation of Chris. So you can see that the permutation of everything is the combination of permutation start from one of the name here. So you can divide in this way into sub-problem. Okay, so there's a combination start from here, then every permutation start from Tom, start from this one, we end with the permutation of this one. Okay, we can use these characteristics to solve this problem using divide and conquer strategy. So use our earlier notation, that means for Si. Okay, initially when we first start, we will be combining for one element, it will be the permutation of first elements. The permutation is start with first element, we end with the permutation of the remaining elements. So here have so eventually, if you keep doing this way, then after that, to solve the permutation of this, again we can use the same concept. In other words, if we have a set S, initially S1 to Sn, so the permutation, the arrangement all the arrangement between S1 of all elements in the set, the permutation of all the elements here is is S1 plus together with S1 star, okay, S2, S2 star, S3, S3 star, Sn, Sn star. Okay, so we split the permutation of all the elements here into n parts, into n parts. Okay, the first one, start from S. Okay, so each of them certainly we have quite a number. So the first part start from S1. The second part start from S2. Those start from S1 will end with S1 star here. S1 star here means, according to the definition earlier, S1 star is S2, S3 until Sn. S2 star is S1, S3, S4 until Sn. This one is big S, capital S. These are the small s. Okay. So S1 star is the subset of elements here excluding S1. So that means what we need to do is for those start from S1, it will end with one of the permutation of this set that exclude S1. Okay? So in other words, we can decompose the original problem into sub-problem, into all these sub-problems. So that is mu Si. Okay? So until then this sub-problem to find out the permutation. So what we need to do is, for this case, we need to do is S1, the first element, then we find out all the permutation of this set, S1 star. So each permutation prefix with S1, okay, will form a final permutation. Okay, so when we split into two parts, this is called prefix. In front, this part is prefix, and this is a suffix. So then we will do it this way. The prefix is always in order, and suffix we have to find out. So prefix plus Si. Okay, then every round we take a look at example. Okay, that means why find it this way? You look at this example. Okay, we want to find the permutation. We just based on three elements, A, B, C. Okay. So initially we have not found anything yet. So this prefix is empty initially. Then so the first step is to take one element out. Take the first element out. That means those permutations start from A. Start with A. Okay. Then we find out the permutation of two elements, B, C. That means the whole set excluding A. So these are the, okay. So in order to find the permutation of 3 elements, okay, we combine the permutation of all these together in order to find the permutation. This is n elements. In order to find all the permutation of the n element, we find the permutation of those start from first element. And after that, we find the solution of those start from second elements, start from third element, etc., and put them together. So for this case, you can see from here, okay, for those start from A, we find all the permutation of BC. For those start from B, we find all the permutation AC. Okay? That means the whole set excluding B. For those start from C, we find all the permutation between A, B, and we put them together. So this is the algorithm. Permute, prefix, suffix. So in order to form permutation of a complete set from subset, okay, so we have to structure the algorithm, the argument in this way. So initially the suffix, when you first call the algorithm the suffix, because all the elements is under S, so suffix is the full set and prefix is nothing. So we will then every time we will solve this problem. In other words, for this case up to n elements, so we will okay, this is the whole problem. This one will be the suffix. Okay. Then for each element is suffix, we find the permutation, then add on. For each element is in this set. So altogether n elements. So once you do this way, you divide the problem into n subproblem. So every time you divide the problem into n subproblem. N subproblem, 1, 2, 3, multiple subproblems. So we are using reduce and conquer. We are using divide and conquer to solve this problem. So to solve this problem, we divide it into 3 subproblems because there are 3 elements here. 1 here, start from 4. Okay, find for those start from A, find with those start from B, find from those start from C. Okay, so this is the algorithm designed from divide and conquer approach. So we solve one problem from multiple subproblems in this case. So in this case, at the end, we find all the permutation. Eventually, when the suffix is empty set, the prefix is one of the permutation, is one of the answer. Because the suffix is all empty set. When you reach here, if you execute this algorithm, step through these algorithms. Okay, so there's a lot of recursion. There's a lot of recursive call. So in this case, you can see how many recursive call. In order to find 3 elements, 1, 2, 3, 4, 5, all these are recursive call. All the permute here, all are recursive call. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 5. Altogether 15. There are 15 recursive call. Okay, now talk about multiplication of integer. Okay, so finding permutation can also be solved by using divide and conquer approach. Okay, do multiplication. Everybody know how to do multiplication. So, okay, so in this case, you have to do a lot of single-digit multiplication. In order to multiply this number, you have to do a lot of single-digit multiplication. Altogether, you have to do 4 here. Every one of them have the time. So here is 5 digit, here is 4 digit. So for every one of them, you have time 5. Then you do 4 times. So altogether, there are 20 single-digit multiplication involved. So Galois multiplication. Galois multiplication is one of the multiplication that so it's written in the table. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5 times 6, 7, 8, 9. Okay. So just how what we have done previously is using the common multiplication. Okay, multiply them together, get this figure. So, and if we use Galois multiplication, it will be clearer. Okay, here 6 times 1, you get 6, right? 6. Here is to put the second digit. So the table, you draw a table according to number of digit. This one multiply this one. So, and every box here is to be divided into 2 boxes by diagonally. So 6 times 2 you get 12, right? 6 times 3 you get 18. 18. 6 times 4 you get 24. 6 times 5 you get 30. Okay? So this is Galois multiplication. 7 again do the same thing. 7 times, okay, 7 times 1, 7 times 2. So the first digit will be, is to be written here. Second digit will be written here. 7 times 5, 35. 3 here, 5 here. Accordingly, the rest accordingly. Okay. So if we use the Galois multiplication, then the computation will be more systematic. Then after that, we add up together. We add up together diagonally. 5, follow this one, you add up together 5. Follow this one, add up together 10. Then this one 21, all add up together. Yeah. Firstly, you add up all together. Then secondly, then you do the carry forward. Okay, firstly you add up all together. All together is 10. So since here is 10, right? It's 10. So you have to carry forward 1. This 1 have to carry forward. This 1 carry forward, that means 1 have to be added to here. That will become 22. 1 added here become 22. So, and 22 will be here. 2 will be written down here. And 2 and 22, the first 2 will carry forward again. Carry forward, carry forward, carry forward. This way you carry forward. Then you get the result. So just now, because this one add up together 10, right? Then, so 0, leave it here, and 1 carry forward, 1 carry forward, add up. Initially, all this add up together is 21. So since 1 carry forward become 22. So here 2 and 2, and the first 2 will carry forward again, continue again. So all carry forward. At the end, when you come to here, the carry forward will be here. You carry forward here. Carry forward here, here, here. Okay, so this way is also 20 multiplication, 20 single digit multiplication, 4 times 5. So you read the result, read this way, top, down. can we make it faster? Make the multiplication faster. Faster means reduce the number of single digit multiplication. So the example here is to show you that we can reduce the number of multiplication here by using divide and conquer approach. Yeah. But I don't know why. I don't know why they want to use this example. I don't quite like this example actually, because in order to introduce the concept, firstly you have to you are burdened with all the steps in Jorosia multiplication. So here again, to make it faster, you need some method. So instead of 20 multiplication, single digit multiplication, we want to reduce it to less than 20 multiplication, single digit multiplication. So what we do here is, any multiple digit can be split into two roughly equal parts. Okay? So we are using the fact that if you have a number, you can roughly divide into two parts, this part and this part. Okay? So this is the first part, and this is the second part. This is the first part, 1, 2, 3. Second part is 4, 5, 6. Okay? So here, that means both are 3 digits. If you have odd number of digits, then you may divide into two roughly equal parts. May not be exactly equal. The first part may be 2, second part may be 3. Okay? If we have 5 digits, so it's usually we will have less digit for the last part and more digit for the first part. Okay, then this means that if you divide into 2 parts, I mean this number is equal to 1, 2, 3 times 1,000 actually, plus 4, 5, 6 times 1, right? You can see this number is roughly this way. So then 1,000 okay, we can use this to make multiplication faster. So the idea is multiply two numbers A, B, and C, D. Okay, so all the numbers we divide into 2 parts A, B, C, D, and where A have A, C. So when you have two numbers to multiply, we have to we cut two numbers into cut both into 2 parts. So in this case, we want to multiply these two numbers. So the first one we cut into A, B, 2 parts. So in this case, here means this is A, this is A, and this is B. Cut into A, B, and the other one cut into 2 parts, also C, D, 2 numbers. So AC must have the same number of digits, and BD must have the same number of digits also. So assuming that AC have K0 digits and BD have K digits, then AB, essentially AB is to express as just something like what we do here. Okay? So if C, since B here, B and D have K digits, so if you express the number in this way, that means for AB, the value is actually A times 10 to the power K. This way. Okay? So here we have K. Okay, K we have how many digits? 3, right? 3. Here 3. Okay. Here means K is K0 is 3. K0 is number of digit in the front part. K is the number of digit, the last part. So front part we have 3 digits. Last part we also have 3 digits. Okay. So here, that's why this number is, the value of this number is 1, 2, 3 times 10 to the power 3. 10 to the power 3 is 1,000. Okay. So plus B. B is the exact number here, the second part. Okay. So in general, if we divide in this way, AB is, the value of AB is A times 10 to the power K plus B, the value of AB. And likewise, the value for CD. Okay? So we consider this number and we express it, we will get a formula. We get this formula, expand it all the way, we get this formula. Here, time it out, and the last term, we expand it. Then after that, we combine the term with 10 to the power k. 10 to the power k. This one times this one, we get this one, we get 10 to the power k. So we combine 10 to the power k together. Okay, this one, we get quite a number of multiplication. So this is still not our final formula yet. We split each number into 2 parts, result into 4 multiplication. Here is still 4 multiplication. We have to cut down the number of multiplication. Okay, now we consider the multiplication of this one, a plus b times c plus d. So if you time it out, you'll find that this is this expression, okay? And a times c, we multiply everything out, we get this 4 terms. 2 times 2, we get 4 terms. Then we have, so from here we can see a times d plus b times c here. This term is equal to, we leave this one, a times d plus b times c is equal to this one. Subtract away this one and this one. We just rearrange the formula to get the value for this one. Okay, now we substitute this one into the earlier formula, the formula in last page. A times b, ab times cd, we get this. So now, you can see that now this part, although there's quite a number of in single digit multiplication, we can express this part, we can convert this part using this formula. Because this part, this one, is equal to this one from the expansion here. This part is equal to this one. So we substitute this one in. Substitute this one to here. So we get this. So here you can see that we only involve less. So what we need here is b times d, right? A times c, two single digit multiplication. A times c, this is also a times c, although there are more terms here, but same multiplication. That means one single digit multiplication. Here is also a times c, right? Also count as single digit multiplication. Both the same, a times c. Okay. Does not involve additional multiplication. Here b times d here. B times d here, here is also b times d. This is not extra multiplication, it's the same. So 1, 2, 3. So earlier we have 4 multiplication. Now, after we express in this way, we only need 3 multiplication. Okay. Time 10 to the power something is not considered as a multiplication. Single digit, we didn't count single digit. We want to reduce a single digit multiplication. Here. A times c, what we need is a times c and b times d, that's all right. The next one is a plus b times c plus d. So 3. This one, a times plus b times c plus d, and b times d, 3 multiplication altogether. Okay. So we are going to use this to make the multiplication faster. So we need only 3 multiplication in order to calculate to multiply 2 numbers. Earlier we need 4 multiplication here. So we can use this recursively until we reach all the single digit multiplication. So there's an example here. If we multiply this number with this number, 4 times 4. They are altogether 16 multiplication, single digit multiplication. So now, by using the method, using the earlier formula, we can reduce it to a low number of single digit multiplication. Okay, so we divide. You can see we divide. In order to divide, we have to calculate. Okay, we divide the number that we need to multiply into 2 parts, right? So we divide into 4, 3, 2, 1. Four, 3, 2, 1 time 5, 6, 7, 8. In order to, we don't multiply directly, that involves more single digit multiplication. We divide into part. This A, B, this C, D. We divide. This A, B, C, D. We divide into 2 parts. So every time we need to calculate, instead of calculating directly, we calculate A times C here, B times D, okay? And A plus B is how much? A plus B, 43 plus 21, 43 plus 21, then we get 64, A plus B. And C plus D, you get 134. So we do 3 multiplication. Instead of multiplying these 2 numbers, we do, here we do this, we divide into these 3 multiplication. So one problem, original problem, to multiply this one, instead of solving it directly, we divide into 3 sub-problems. Multiply this one, multiply this one. So this is the use of divide and conquer. In some detailed step, I think I leave it to you to go through. So after that, how to calculate it. So that means we will calculate this number, this value. After I use them together to form the solution for the whole problem. We have to calculate this value. So calculate this value, and this value, and this value. Okay, we calculate the value. The same thing, we divide again. We divide. So 1, 1, we divide into 1, 1, then we multiply. So A times C, we divide into 1, 1. A times B, A, B, C, D. So A times C, B times D. Then A plus B, A plus B, that's 7. C plus D, that's 11. We calculate. So we will calculate. Instead of calculating this number, we divide into 3 sub-problems to calculate this one, this one, this one. This one is very single digit. Okay? You don't need to divide any further. We divide everything until single digit. So every time we divide, instead of computing the number, computing the answer, we divide into multiple sub-problems. In this case, we always divide into 3 sub-problems. Okay? So I will not go through all this detail. There's one question in tutorial. It will ask you to find. So the main idea is that here we make multiplication faster by using divide and conquer approach. Okay, so earlier we said that we need to calculate this one, A times C and B times D, right? B times D. Then we need to calculate this number. So once this number are calculated, how to form the answer for the original answer is the way to form it using the earlier formula. So here we have 2 digit, right? 2 digit here. 2 digit means 10 to the power 2. 10 to the power 2. So we just, after we get the answer for this, and we just substitute using this formula. We just use this formula. Okay, use this formula. Divide into 2 parts. Okay. After you so you need to calculate A times C. And this answer for A times C. For A times C, you will be times 10 to the power 2k. K depends on how many digits in B. Here, B and D have k digit. Okay? The question we have, the second part have how many digits? 2 digits, right? 2 digits, 10 to the power 2 times 2, 10 to the power 4. So A times C times So we just use this formula. After you work out all this, A times C, B times D, A times C, B times D, and A plus B times C plus D. After you work out this, then we just make use of this formula. Just substitute into this formula to calculate the result. Okay. Use this formula. So that's what we have in the last slide. Okay, so we work out the answer for this one, A times C, right? Work out the answer A times C. And B times D, A plus B times C plus, we work out these three multiplication. Once we work out this multiplication, we can use a formula. So A times C, that's 20. That one have to times 10 to the power 2k. 2k, our k here is 2. K here is 2. So 2k means 2 times to the power 2 times 2, 4. 1, 2, 3, 4. That's why it's 1, 0, 0, 0, 0. And here is 10 to the power 2. 10 to the power k. Okay? And this is A times C. These two number multiplication. A times C. And this is B times D. B times D. This number, B times D is this number. Okay? And the center part is A plus B times C plus D. A plus B. Okay? A times, okay, this one, so it's 21, 64. A plus C. So altogether 64 times this one plus it. So it's this value minus away this value, and this value. If you follow the formula, this is here we use the formula I have just shown you to calculate this result. At the end, we find this result. So that means we solve one problem by dividing it into 3 sub-problems, and we use a solution for the sub-problem together to form the solution for the whole problem. So altogether, you will count the single-digit multiplication. Altogether, there are 13 single-digit multiplication. Okay, I suggest you go back, you go through the detail. All this multiplication, certainly you have to, in order to fully understand it, I just give you an idea. In order to fully understand it, you have to go through you have to follow it. You have to try to,
Is it required to, based on the exam question, if it's such a thing like this, right, is it required for us to remember the formula, memorize the formula?
If exam was such question, certainly you need to understand the formula very well. Otherwise, you can see from here how to, if you don't understand, you cannot apply.
So if you understand, then you can start off with the comprise formula, then you can expand out of there.
Yeah.
Then you can get the answer. Then you can use that as the basis of your formula to calculate the answer. Is that what you said?
Yeah.
Okay.
Okay, if you have such questions, certainly you have to memorize the formula.
Right.
Yeah. If you have such question, because the formula is not a kind of okay, let's say basic property of logic. De Morgan rule is not the kind. So, and this is just a formula introduced to solve this problem. It's not a so-called well-formed formula. But I did not say that it will be such a question. But earlier I also highlighted, I don't know why you want to use such example to introduce the concept of divide and conquer. It's something like a small, a very small capacity car. Why you want to install a very powerful aircon? I don't understand why the reason they want to introduce this example here. But anyway, it is part of the material. So we introduce it, but the main thing in this unit is that you have to understand what is reduce and conquer, what is divide and conquer in solving problems. I guess that is not difficult to understand, right? Cannot understand.
No, I mean, it's not difficult to understand. It's no
Yeah.
difficult.
Yeah. So and reduce and conquer and divide and conquer is closely related to induction, right? Because under induction we also talk about forming a solution of smaller subproblem, right? So certainly they are related. And in fact, if you look at it, which one is cover? Which one cover which one? Induction. Induction, we always talk about solving problem from smaller subproblem, right? So you may solve things like cover the ball, 2n by 2n ball. We divide the whole problem into 4 subproblems, right? So that is the divide and conquer. Yeah. That's the way I use the divide and conquer. Then another problem is Tau unknown here. Tau unknown, you solve the bigger problem by reduce and conquer. So in fact, induction cover both divide and conquer and reduce and conquer. Divide and conquer and reduce and conquer focus on problems, focus on decomposition structure. But induction is a general problem solving technique. Okay, the more important thing is to understand it, and the more important thing is to understand it, and understand after you understand how to use them, and after that how to specify as algorithm. Algorithm will be mainly recursive algorithm because reduce and conquer, divide and conquer, and also induction. The easier way to specify them is using recursive structure. Okay. After this, we will proceed to the next unit, sorting and searching.
Only time I use this is that I know the code or something.
Why is it 10 to the power of 4?
10 to the power 4.
1,000.
Oh, yeah.
Should be 3, right?
Yeah.
He goes so fast.
Using this formula, after A times C, the first part of the two number timed together, you have to time 10 to the power 2k. All of this one 10 to the power 2k.
So it's always 10 to the power of 2k.
Yeah, this formula. So what is the k for our calculation just now? What is the k?
2 zeros.
Huh?
Is it 2 zeros?
K is 2.
No.
Because you divide into 2 digit. Number of digit. K means number of digit in B and D. Okay. So here, K means B and D.
What?
B and D. B is here. B 21, 2 digit, right? 2 digit K. B, this B. And this is D. This 2 digit also. Each of them have 2 number of digit.
So it's based off the splitting of the it's based on the number
Yeah,
of
just now
first bit.
the formula, after you split, you can see the formula, yeah. So this is so k is 2. K is 2, right? So, and just now the term you have seen is 10 to the power 2k, right? So k is 2. 10 to the power 2k. Now k is 2. K is 2 means 10 to the power 2 times 2. 10 to the power 4.
Can go to slide 40.
4, 2,
40.
4, 0.
One, two, three, 4. The sixth line, calculate 0, 7 times 1 and 7 times 2. Can you explain that part?
Oh, this is divide again. In order to calculate these two numbers, this two number is not single digit multiplication. Once it's not single, you will divide. So divide into 2, 2, into 1, 1. Here, so in this case, we divide into AC. A is, in this case, A is 0.
Okay.
There's nothing here, right?
Yeah.
So it's 0. If it's nothing, it's 0. A is 0. And C is 1.
So 7 times 1.
Yeah.
Eight times
B is 7. D is 1. AC, since A is 0, so 0 times anything will be 0.
Yeah.
And B times D, B is 7. D is 1.
Yes.
So 7 times 1. B times D.
Then the 7 times 2?
A plus B times C plus D. A plus B, A plus A, B. A is 0. B is 7, right?
Yeah.
So A plus B is 7. 0 plus 7, 7. The two part plus together. So C plus D. C plus D is 1 plus 1, 2.
2.
So the last one is A plus B times C plus D.
Okay.
Because the formula here need A this because of the formula here. A plus B times C plus D.
Where does 7 times